In our earlier lecture, we have introduced the idea of sufficiency. In the present lecture, we are going to introduce another important concept which is called completeness. Together with sufficiency, completeness plays a very important role in finding uniformly minimum variance unbiased estimators. In our present discussion, first we shall define the completeness in relation to a family of probability mass functions or probability density functions. Then we shall define the idea of a complete sufficient statistic. Our discussion will be supported by several examples which are relating to different distributions which are used in practice. In the present module, we shall discuss the completeness of a family of probability distributions. Consider a family of probability distributions script f theta equals to set of all f theta x such that theta belongs to script theta. Let psi x be any real valued function of x having finite expectation. We say that the family is complete if expectation under theta psi x equals to 0 for all theta implies that probability under theta psi x equals to 0 is equals to 1 for all theta. The family script f theta is called boundedly complete if for any bounded function psi x of x, expectation under theta psi x equals to 0 for all theta implies that probability under theta psi x equals to 0, this probability is equals to 1 for all theta. Next, we discuss the completeness of a statistic. Let capital T be a statistic and script ft be the family of probability distributions of T. The statistic capital T is said to be complete or boundedly complete if the family of distributions of T is complete or boundedly complete. That is, for any real valued function psi t having finite expectation, expectation under theta psi t equals to 0 for all theta implies that probability under theta psi t equals to 0, this probability is equals to 1 for all theta. The implication of a statistic T is complete that there exists no non-trivial function of T which is an unbiased estimator of 0. Now we discuss some results on completeness. Result 1. If T is complete and T star is a function of T, then T star is complete. Proof. Let T star equals to phi t and psi T star be any real valued function of T star. Expectation psi T star equals to 0 for all theta implies expectation psi of phi t equals to 0 for all theta implies psi of phi t equals to 0 for all theta with probability 1 since T is complete, which implies that psi T star equals to 0 for all theta with probability 1. Hence, T star is complete. Next, we consider another result. Result 2. If T is complete, then T is boundedly complete. Proof. Let psi t be any real valued function of t. Now, expectation of psi t equals to 0 for all theta implies that probability psi t equals to 0 is equals to 1 for all theta. Then it must also be true for the subset of bounded functions. It is to be noted that the converse of this result is not true. Let us consider the following counter example. Let capital X be a random variable with PMF. F theta x equals to theta if x equals to -1 equals to 1 minus theta whole square into theta to the power x if x equals to 0, 1, 2 up to infinity, where 0 less than theta less than 1. Let psi x be any function of x such that expectation under theta psi x equals to 0 for all theta, which implies theta into psi minus 1 plus summation over x from 0 to infinity psi x into 1 minus theta whole square into theta to the power x is equals to 0 for all theta, which implies summation over x from 0 to infinity psi x into theta to the power x is equals to minus theta into psi minus 1 whole divided by 1 minus theta whole square, which is equals to minus summation over x from 0 to infinity psi minus 1 into x into theta to the power x for all theta. Comparing the coefficients of theta to the power x for x equals to 0, 1, 2 from both sides of the above identity, we get psi x equals to minus x into psi minus 1 for all x. If psi minus 1 equals to c not equals to 0, then psi x equals to minus cx for all x. That is, psi x is non-zero with non-zero probability. Hence, the family of distributions script f theta equals to set of all f theta x such that theta belongs to script theta is not complete. Again, psi x is bounded if and only if psi minus 1 equals to 0, in which case psi x equals to 0 for all x from 0, 1, 2 up to infinity, and hence the family of distributions script f theta is complete. Next, we discuss some examples. Example 1. Let x follows binomial distribution with parameters n and theta. Consider any real valued function psi x such that expectation under theta psi x equals to 0 for all theta, which implies summation over x from 0 to n psi x into ncx into theta to the power x into 1 minus theta whole to the power n minus x is equals to 0 for all theta. If we set lambda equals to theta by 1 minus theta, then summation over x from 0 to n psi x into ncx into lambda to the power x equals to 0 for all lambda greater than 0. which is a polynomial in lambda of degree n. The only way a polynomial of degree n can be 0 for more than n distinct values of the variable is for all coefficients to be 0. That is, psi x equals to 0 for all x from 0 to n. Thus, we have seen that if expectation of psi x equals to 0 for all theta, then psi x equals to 0 with probability 1. Hence, the binomial family is complete. Consider the following remarks. Remark 1. If the parameter space script theta is not an open interval of real line, for example, if script theta contains only 2 points 1/3 and 2/3, then the family of distributions of x is not complete. Remark 2. Let x1, x2 up to xn be IID Bernoulli theta random variables. Consider the statistic capital T equals to summation I from 1 to n xi. T follows binomial n comma theta. Then T has a complete family of distributions and hence T is complete. Now the joint PMF of x1, x2 up to xn is given by f theta x1, x2 up to xn is equals to theta to the power summation xi into 1 minus theta whole to the power n minus summation xi, where xi equals to 0, 1 for all I. The family of joint distributions of x1, x2 up to xn is not complete, since if we take psi x1, x2 up to xn equals to x1 minus x2, then expectation of psi is equals to expectation x1 minus expectation of x2, which is equals to 0 for all theta, but probability under theta x1 minus x2 not equals to 0, this probability is greater than 0 for all theta. Next, we consider another example. Suppose x1, x2 up to xn be IIT random variables with common PMF fx equals to 1 by capital N, where x equals to 1, 2 up to capital N. N is a positive integer. Let psi x be any real valued function of x such that expectation under n psi x equals to 0 for all n greater than equals to 1, which implies 1 by capital N summation over x from 1 to capital N psi x equals to 0 for all n. And this happens if and only if psi x equals to 0 for all x equals to 1, 2 up to n. Hence, the family script fn equals to set of all fnx such that n greater than equals to 1 is complete. Now, suppose that we exclude the value capital N equals to small n naught for some fixed n naught greater than equals to 1 from the family script fn. Let us write script fn star equals to set of all fnx such that n greater than equals to 1 and n not equals to n naught. The family script fn star is not complete. To show this, we consider the function phi x equals to 0 if x equals to 1, 2 up to n naught minus 1, n naught plus 2, n naught plus 3 up to infinity, equals to c if x equals to n naught, equals to minus c if x equals to n naught plus 1, where C is a non-zero constant. Then expectation of phi x equals to 0 for all n greater than equals to 1 and n not equals to n naught. But probability under capital N phi x equals to 0, this probability is not equals to 1 for all n. Hence, the family script Fn star is not complete. Note that this example shows that the exclusion of even one member from the family script Fn destroys completeness. Next, we consider another example. Suppose x follows normal with mean theta and variance 1. Consider any real valued function psi x such that expectation under theta psi x equals to 0 for all theta belongs to real line, which implies integration minus infinity to plus infinity psi x into 1 by root 2 pi into e to the power minus half x minus theta whole square is equals to 0 for all theta, which implies integration minus infinity to infinity psi x into e to the power minus x square by 2 into e to the power theta x dx equals to 0 for all theta. Since the integral is a bilinear Laplace transform type, we get psi x into e to the power minus x square by 2 is equals to 0 for all x, which implies psi x equals to 0 for all x, and hence the family normal theta comma 1 is complete. Next, we consider another example. Suppose x follows normal distribution with mean 0 and variance theta square where theta greater than 0. Now, if we take psi x equals to x, then expectation of psi x equals to 0 for all theta, since the integral is an odd function of x. But the function psi x not equals to 0 with probability 1. Hence, the family normal 0, theta square is not complete. We consider another example. Let x1, x2 up to xn be a random sample of size n from normal distribution with mean 0 and variance sigma square, where sigma is unknown. Consider the statistic capital T equals to summation I from 1 to n xi square. Since T by sigma square follows chi square n, the density function of T is given by gt equals to some constant into e to the power minus t by 2 sigma into t to the power n by 2 minus 1, t greater than 0. Now, for any real valued function psi t, expectation of psi t equals to 0 implies integral 0 to infinity psi t into e to the power minus t by 2 sigma into t to the power n by 2 minus 1 dt equals to 0 for all sigma greater than 0. Since the integral is a Laplace transform type, it follows that psi t into t to the power n by 2 minus 1 is equals to 0 for all t, and hence psi t equals to 0 with probability 1. Hence, t is a complete statistic for sigma square. Next, we consider another example. Let x1, x2 up to xn be a random sample of size n from rectangular 0 theta population. Let t equals to x ordered n, which is the maximum value of x1, x2 up to xn. The PDF of t is given by g theta t equals to n into t to the power n minus 1 divided by theta to the power n, where 0 less than t less than theta. Now, for any real valued function psi t, expectation under theta psi t equals to 0 implies integration 0 to theta psi t into t to the power n minus 1 dt equals to 0 for all theta greater than 0. Differentiating both sides by Leibniz theorem with respect to theta, we get psi theta equals to 0 for all theta greater than 0, and hence psi t equals to 0 for all t greater than 0. Since the interval 0, theta is a subinterval of 0, infinity, we get psi t equals to 0 for all t belonging to the interval 0, theta. Hence, the statistic t has a complete family of distributions and therefore t is complete. In our present lecture, we have seen that a statistic capital T is complete means that there does not exist any non-trivial function of t which is an unbiased estimator of 0. We have also seen that if t is complete, then any function of t is also complete. If a statistic capital T is complete, then it is boundedly complete, but the converse may not be true. The binomial family with parameters n and theta is complete when theta lies on an open subinterval of 0, 1, but when it can take only two values, say for example 1/3 or 2/3, the family is not complete. We have also seen that even the exclusion of one member from the family destroys its completeness. We have seen that the normal family with parameter theta and 1 is complete, though the normal family with parameter 0 and theta square is not complete.